Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on September 7th, 2025, which was about 3 days ago. The headline result is efficient text-to-image generation at 1024 by 1024, quality trained for roughly $535 to $620 on 4 RTX 5090 GPUs, thanks to a compact architecture and training recipe. The paper is titled Homemade Diffusion Model from Scratch to Hatch, and as we will see later, the implications for budget-friendly training are quite significant. The work centers on a cross-U transformer design, token routing acceleration, shifted square crops, and progressive resolution scaling to deliver strong images and even intuitive camera control. On X, the author announces the early technical report and promises more ablation and experiment details on architecture choices soon, drawing modest interest with about 106 likes and a reply. Alright. The previous figures set the stage for training efficiency. Figure 1 presents the full pipeline, which starts with captions encoded by QN30.6B, and images pass through the shifted square crop to produce position maps and aspect ratio signals. The left panel summarizes these inputs flowing into the HDM core. The right panel details the cross-U transformer path with token routing acceleration. Tokens concatenate with text and position features, go through transformer blocks, undergo tread selection, pass XUT, then merge and decode, so the model saves compute without sacrificing composition. Alright, the previous figure outlined the full pipeline with token routing. Figure 2 shows the cross-U transformer backbone, which stacks encoder blocks on the left and mirrors them with decoder blocks that pull features through cross-attention skips. The central panels zoom into an encoder block and a decoder block that inserts a cross-attention transformer where skips land, so the decoder can query only relevant encoder features. The right panels detail the transformer block and the adaptive layer normalization unit, which modulate activations using conditioning signals. So the previous figure detailed the backbone blocks and conditioning. Figure 3 illustrates the shifted square crop workflow, which prepares arbitrary aspect ratios without complex bucketing. The left panel shows a latent with height and width, then a resize sets the smaller side to X while a position map is generated to encode coordinates. The middle panel highlights that crops can shift over the resize latent, so training sees many views of the same image. The right panel shows the final X by X crop paired with its matching position map for diffusion training. So the previous figure walked through shifted square crops. Table 1 summarizes the 3 cross-U transformer scales, which target different budgets while keeping the sequence length fixed at 256. The base model uses dimension 1024 with QN30.6B text, 16 attention heads, and totals 20 transformer blocks for about 343 million parameters. The small and large variants bracket that with 230 million and 550 million parameters, so training can match available hardware. Okay, the previous figure explains shifted crops enabling arbitrary aspect ratios. Table 2 lays out the progressive training recipe across 256 squared to 1024 squared stages, which ties datasets, hyperparameters, and wall time together. The early stages used full Danboru to learn broad concepts, while the final 1024 squared stage switched to a curated set for quality and stronger negative prompting. Learning rates stepped down and batch sizes shrank as resolution rose, and tread stayed at 0.5 until the final stage, so full capacity delivered better classifier-free guidance. Wrapping up, 2 takeaways stand out. A compact cross-U transformer with cross-attention skips and token routing hits strong 1024 by 1024 quality, and the shifted square crop with progressive scaling unlocks arbitrary aspect ratios and intuitive camera control, all on consumer GPUs at a few $100s. The broader implication is accessible, high-quality text-to-image research. That is it for the AI Research Roundup. I am Alex. Thanks for listening.